Right. Steady. Hello, my name is Argyris, and I will be presenting the main points from my MRes dissertation, where I worked on the development of an empirical model of summertime temperatures in Leicester homes using the 4M dataset. To start with, the 4M dataset includes the hourly recorded internal temperatures from both living rooms and bedrooms in 230 houses in Leicester between the 1st of July and the 31st of August in 2009. The first step in developing the model was to establish the strongest possible relationship between the external and the internal temperatures. The research showed that the best correlation is given when using an exponentially running mean of the external daily mean temperature, similar to the one given above, which is given in the British Standards BACN 15251. These three figures demonstrate the R-squared values for both living rooms and bedrooms for the best regression line fit of the internal daily mean temperature to the exponential running mean of the external daily mean temperature. Firstly, when using the equation is given in the British Standards. Secondly, by adding the same day's temperature data. And thirdly, by altering alpha to other than the one suggested at British Standards. It is clear from these figures that the best correlation with an overall average R-squared value of 0.9 is achieved when using the equation that includes the same day's data and with an alpha value of 0.6. And having identified the form of the external temperature that results in the best R-squared value, the next step was to develop the model using Spss. The result was a predictive model of the form y equals a plus bx, or else in UK y equals mx plus c, that predicts the internal daily mean temperature for a given running mean of the external daily mean temperature. The coefficients a and b are based on the house characteristics, such as house type and the year it was built. However, despite the promising strength of the correlation mentioned before, when the model includes parameters such as the house type and the house age, the variation explained of the model drops considerably to less than 50%. Therefore, other parameters need to be taken under consideration. Using this developed model and a series of future weather files produced by the University of Leicester as an outcome of the Prometheus project, with the aid of a UK CP09 weather generator, 3 future scenarios were tested in order to explore the summertime internal temperatures of houses by 2030, 2050, and 2080. The results show that by 2080, there could be a 6 degrees increase of peak internal temperatures compared to 2009, and this could have detrimental consequences to the health of the occupants. Finally, a novel approach in predicting overheating was developed based on the empirical data. A series of graphs that allow the prediction of the number of hours within a day above a certain threshold in semi-detached houses were produced. These were named as overheating curves and are presented in the final figure on the right. The way they work is that one needs to decide on the threshold value, say 26 degrees, then obtain the daily mean internal temperature from a predictive model, and finally track the appropriate curve in order to get the number of hours within a day that the internal temperature could be above the threshold. Moving ahead, my aim is to further develop the predictive model and use it in order to map the current and future risk of summertime overheating in UK homes. And some initial objectives are to decide on appropriate modeling techniques, analyze current and future heat waves, and decide how to best model them, decide on how to model each home, the metric used to indicate the overheating risk, run the model for a trial area with and without the refurbishment, future refurbishments, and also finally run the model for the UK stock. Thank you.